So I think we have reached a critical mass, so we can start. Hello, everyone. Welcome to another Vanderbilt Machine Learning seminar. We are very glad to host Yilun Du today. Yilun is a senior research scientist at Google DeepMind and an incoming assistant professor in the Harvard Kempner Institute on Computer Science. Congratulations. He received his PhD at MIT, advised by Leslie Kelbling, Thomas Lozano Perez, and Josh Tannenbaum. His research spans the fields of machine learning and robotics with a focus on generative models. Yilun was a recipient of the NSF Graduate Fellowship and a finalist for Qualcomm and Open Philanthropy Fellowship. Previously, he has done research fellowships, internships at OpenAI, FAIR, DeepMind, and his work has received Best Paper Awards at iClear and at NeurIPS and ICRA workshops. With that, we are very excited to have you here, Yilun. The stage is yours.
Great. Yeah, thanks so much for having me here. I'm really excited to give a talk. And feel free at any point if people have questions to put it in chat, or I can answer them also in the middle of the talk. So today I'll talk a bit about some of the work I've been doing over the last 5 years on essentially trying to generalize a little outside the training distribution. So what does that mean? Well, so overall, my research has really been driven by this goal where we want to get these intelligent general purpose agents in the physical world. So if we look at current robots, we're only able to do very simple tasks. So we can pick up a mug and put it on a rack, or we can pick up one object and place a second object on top of it. But what we really want is we want machine learning systems that can allow us to really get autonomous, intelligent agents in the real world. So we want agents that can robustly generalize to unseen tasks, unseen environments, and other agents. Now, a really big problem in this setting is how can you actually get these systems? How do you get systems that can generalize? So in this talk, I'll point towards a general approach towards this problem, and then I'll talk a bit about some key components and results. So the general approach I'll talk about is how by learning probabilistic generative world models, these models can really give us a very useful tool for generalizing. And I'll talk about 2 ways in which these systems can allow us to generalize. So one is this idea that they really allow us to search at test time. And the second is that we can really compose different generative world models together to construct new models in areas we don't even have any training data over. So let me first talk a bit about the first point. So let's consider a task. Let's say climb up the stairs. Normally, when we have a neural network do this task, the neural network will take an image observation as well as the task and output a single output action trajectory. And this is great when your training and test distributions match exactly. But this becomes really problematic when the environment changes or your predicted action is invalid. So let's say now we have a new constraint that says we can no longer move forward. So if we have a single neural network that just predicts this prediction, we don't know what to do. And one idea is instead of training a neural network to explicitly predict what I should do, instead we should train a neural network that can encode preferences for all possible action trajectories. And this is the idea of learning a probabilistic generative model. So we can use it by learning a generative model over the action trajectories we want to go through in an environment. Then we can really construct the energy landscape over the space of actions. So given an action trajectory, my network can predict high energy if it's unlikely or poor action trajectory, and low energy if it is a good action trajectory. And in this case, the scalar energy represents the negative likelihood or negative utility of the possible action. And the benefit of this formulation is now I can infer the action to execute by now searching. So I have this energy landscape, and I simply run a search procedure to find the action that minimizes my energy. Now, this is really useful for generalizing. So let's say I have a new constraint, such as I want to be safe, I don't want to move forward, or to be safe, I want to move very little to conserve my battery life. What I can do is now I can take this new constraint and encode it as a separate energy function. And now by having the first energy function of climb up the stairs that we've learned before, and by adding it with the second energy function, if I jointly run the search procedure on this composed energy function, now we can get predictions that satisfy both of these constraints. So one way to view using generative models to do predictions is that instead of explicitly instead of learning a deterministic model that explicitly gets you predictions, generative models allow you to use search to get a solution, and this can really be very useful to allow you to generalize to new settings. Although one trade-off is that it is a bit slower. So that's the first idea. These world models really allow us to do search. The second idea is that these generative models can really be built compositionally. So we've all seen in the last couple of years that generative models, such as language models, are able to do really fascinating things. So if you ask a language model how to construct AI, it can give you these step-by-step instructions. But at the same time, if we look at multimodal language models and we give them even simple images and simple questions, they actually perform very poorly. So one thing that is, so why is that? Well, I think one thing we can look at is really the distribution of data we have. So natural language is constructed by people, and it's a synthetically made language where we see all types of different combinations of words and languages, making it so that the training and real-world distributions are fairly close to each other. In contrast, if we consider embodied data, such as the data a robot may see, or the data of the previous images we've seen, really the data on the internet is only a really narrow slice of the entire real-world distribution we would like our model to operate over. So many settings, such as pixels and images and embodied data, are just much more complex and are a setting where the training distribution just does not cover the entire real-world distribution. So what I'll talk about is this idea that we can build generative models compositionally using using the energy function abstraction. And this can really allow us to generalize a bit outside of this narrow slice of training distribution. So the overall idea is we're going to learn one generative model to capture one axis of the distribution, and we can learn a separate generative model to capture a second axis of the distribution. And these generative models don't have to actually be like these independent axes. These generative models could also be like pairs of variables. So we're just encoding these generative models encode some type of independent structure about the distribution. But one idea is that by learning these generative models over these simpler portions of the distribution, such as this axis, the first axis, or the second axis, now when we compose these generative models, we can actually generalize to these areas outside of just the training distribution, as long as every single individual factor is in distribution. And of course, when we construct a generative distribution in this factorized way, we're making some independence assumptions. So we assume that that the effects of this axis may be independent of the effects of the second axis, which will lead us to have biased estimates outside this training distribution. But one thing is, in the real world, a lot of the world is actually independently structured. And this gives us a reasonable estimate, which may not be perfectly accurate outside of the training distribution, where otherwise you can't get an estimate at all. I'm going to now present another argument. So we've all seen that over the last some number of years, generative models have gone from looking like DC GAN, where the images look super low res, to what we've seen recently was these text-to-image models, where all these images look fascinatingly photorealistic. So one argument that some people make is, well, instead of trying to build these generative models compositionally, why don't we just try to gather all the possible data in the world? So one thing to note is that over the years, generative models haven't simply gotten larger. They've also there's also been a series of really complex engineering tricks that have been done to make them look much better. So one really big trick is this idea that we should make generative models model simple conditional distributions. In 2015, we were just modeling the unconditional distribution of images. In 2018, we started modeling the class conditioned distribution of images. In 2022, and very recently, we've been modeling the distribution of images or videos given complex text descriptions. And now when you have this problem where you give this very complex text description, the generative modeling task becomes much easier because the model just has to model a much simpler conditional distribution. And another really big change over the years has been this idea that we learned a probability distribution using our generative model, and we use and then we really try to tweak the distribution we want to sample from at test time so that we can get better samples. So in 2018, we started doing this type of mode dropping, where we tried to really only sample really high likelihood samples. In 2022, we started sampling from this composed distribution, where we really tried to emphasize images that look maximally aligned to your text. So if we take all these hacks away and just look at what the generative model itself looks like, we can take the stable distribution model, which is able to generate these really photorealistic images, and we can just sample from the actual text condition distribution learned by the model. And we see that even if we just sample from the distribution learned from the model, the images look a lot worse. And we can we can actually just sample from the unconditional distribution. So we stop sampling from the text condition distribution, and we just sample from the unconditional image distribution. And now the samples look even worse. So really, even though we have started training these models on more and more massive amounts of computational skill, it's not the case that these models just with more skill just spontaneously can generate more higher and higher resolution images. Rather, generative models can really only fit really high dimensional distributions that are rather simple. And the way we've done this in the past is by just richly conditioning the generative model on complex prompts like text. And one way to think about what I'm talking, the rest of this talk on compositional generation is that it's one way to really tractably represent really high dimensional distributions. So if we have a really complex distribution, we can simply learn to model each factor of the distribution, and each of these factors will be much simpler than learning the entire multimodal distribution. Cool. So that was a brief intro on how generative world models can really help us generalize. So now I'll talk a bit more about some key components and results. So this talk will have 4 parts. So first, I will introduce the idea of energy-based models, and then I'll talk about the way they can be composed together. I'll then talk about how they can be used for planning. And finally, I'll talk about how they can really be combined with existing foundation models to combine them together for intelligent decision-making. So first, let me give a little background on energy-based models. So energy-based model is essentially a model that's defined by energy function. And the overall idea is, let's say we have energy function for red trucks. This energy function will assign things that are not red trucks, like this green truck over here, high energy. And it will assign images of red trucks low energy. And this energy function essentially captures this high dimensional function over the captures this energy landscape over the space of images. So every single point in the space of images will be assigned to energy, where only the images that are red trucks will be assigned low energy, and all other images will be assigned very high energy. And now this energy function can encode many different things. So on one hand, it could encode the utility of an action, somewhat similar to the example I showed earlier in the talk. It can be used to encode whether you're inside a set or not, where all points that are inside a set have low energy and all other points have high energy. And in general, and more broadly, it can be used to encode any type of unnormalized probability distribution. So through the Boltzmann distribution, you can define a probability distribution from this energy function. So now one question is, let's say you have an energy function. How do you actually draw samples from it? So if you naively try to find samples from this energy function, it can actually be kind of difficult because as your space, when your data space is really high dimensional, there are exponential number of points possible in this space. So it will be very hard to find one that has low energy. So one big idea is you can really use a neural network to help you guide your sampling. So let's say I want to generate a sample from my neural network. What I can do is I can initialize my sample from random noise, and then I can use the gradient of the energy function to really help you refine and improve the sample. Issue with the previous approach, though, is it doesn't really allow you to sample from a probability distribution. So in early 2019, we proposed that we should instead use Langevin sampling to really scalably sample from these high dimensional energy distributions. And this is what Langevin sampling looks like. So you follow the gradient of the energy function to help you find a high energy data point. And then added Gaussian noise perturbs you between probability modes, allowing you to explore and find different high likelihood points in your distribution. And if you look at it on the image domain, it ends up looking very similar to what you've seen in diffusion models. And I'll talk a bit about there's connections in a bit. And one way to think about energy-based models is that it really trades off the ability to sample quickly. So in this setting, the sampling procedure or generating images is really slow because we require all these steps of sampling. But the benefit is that we can define any type of energy function. So we can add two energy functions, we can add constraints, and we can use this procedure to sample from any new configuration. So it allows us to generalize and generate from many different new distributions. So how do I actually learn this energy-based model? So let's say I have a probability distribution P of X. And what I want to do is I want to learn a parameterized probability distribution e to the negative energy of X so that this distribution represents the original probability distribution. So we can train this using maximum likelihood training. So if you compute the gradient of the log probability, it corresponds to decreasing the energy of or computing the gradient respect to a single data point, and computing the gradient to the partition function or the energy mass assigned to every other point in your data landscape. And if you do some reductions, what you find is that the maximum likelihood training objective for energy-based models corresponds to drawing samples from the probability distribution and decreasing the energy of those samples while drawing samples from your learned distribution and increasing the energy of those samples. So it's it's similar to a contrastive learning procedure. And this type of training procedure has been used to train energy-based models for several decades. In 2019, we illustrated how by using the Lengerman dynamics, as well as a replay buffer of past samples that you've drawn from MCMC, we can really scale this training procedure to high-dimensional data distributions. So here's an illustration of this procedure. So at the beginning, you have this energy landscape that's completely flat. And what you do is you draw two samples from the energy landscape, which are the green dots here, and you take a ground truth data point, which is the red dot. And now you decrease the energy of these green data points while increasing the energy of the generated sample. Sorry, so red is generated sample, green are ground truth data points. And now you have this evolved energy landscape, and you repeat this procedure where now you sample from this energy landscape, and since it's a bit more shaped now, this generated sample looks a bit more similar to a red truck. And now you repeat this procedure where you increase the energy of this generated sample while decreasing the energy of red trucks. And by running this procedure for a very large number of iterations, you get this energy landscape that has low energy at exactly the points that are red trucks, at which point when you generate samples from the energy landscape, they correspond to red trucks, while the ground truth data distribution also corresponds to red trucks. So now you decrease and increase the energy of red trucks, and therefore you cancel the training and you've converged to your final energy landscape. So now I'll talk a bit more about the connections of diffusion models and energy-based models. So in early 2019, we proposed this sampling procedure where you have this you start from Gaussian noise, and by running this Langevin sampling procedure, you now get these images. You get these images samples. So following our work in 2019, there is subsequent work on score-based models, where they essentially also train an energy-based model, but where the gradient of the energy function is learned by the denoising function. So the sampling procedure ends up being exactly the same. The only difference is you've changed the energy training procedure to be learning the gradient of the energy function through denoising as opposed to this landscape shaping procedure I talked about earlier. And you can really view diffusion models as a type of score-based model where you essentially take the inputs and you contract the inputs over the course of sampling. And so if you look at the sampling procedure, it ends up looking very similar to that of an energy-based model. So overall, you can roughly treat diffusion models as energy-based models, where the denoising function is a gradient of the energy function. And for a lot of the rest of the talk, I will be using diffusion models as a way to train energy-based models. So if you want to compose two energy functions, let's say you want to add two energy functions, you can just add the two denoising predictions from the diffusion model and similarly implement the operation. And then you can also replace the score function of a diffusion model with the energy function. There's a little added complication in the sense that a diffusion model actually doesn't learn a single energy function, but actually the different noise levels of the diffusion process actually learn a sequence of energy functions. I'll talk a bit more about that later in the talk. So in my work, I've illustrated how these energy-based models can represent distributions across a variety of different domains, such as images, robot plans, natural language, proteins, videos, and 3D shapes. Cool. So let me talk a bit about compositionality now. So let's motivate compositionality from how we want to like construct like composable neural networks. So if we want to train a neural network to satisfy a set of properties, let's say I want this neural network to generate trajectories that reach a goal, where the trajectories have a particular gait and where the trajectories avoid obstacles. The way we can do it is we can just define loss functions for each of these properties, and I can just train a neural network to optimize all three of these loss functions. And this allows you to get a neural network that has trajectories that satisfies this set of properties. But the issue is that we can't do this at prediction time. So if I have one neural network that generates trajectories that reach a particular goal, a second neural network that has a particular gait, and a third neural network that generates trajectories that avoid obstacles, I can't just combine the final predictions in a neural network because this isn't really an additive abstraction at test time. So the way you can view energy-based models is a really intermediate abstraction to prediction, which is composable. And the idea is that to generate trajectories that reach a particular goal, we learn an energy-based model that assigns low energy to all trajectories that reach this goal, and likewise for gates and obstacles. And now, since I have 3 energy landscapes as opposed to 3 explicit predictions, I can just add the 3 energy functions together. And now I can run a bit of a lightweight sampling procedure to get a prediction that has all of these properties. So by not modeling the explicit prediction, but instead by modeling the landscape, we now have a way to really combine neural networks and properties together at test time. So on the image, now let's look at the image domain. So if I have a red truck energy function and I optimize the energy function, I get an image of a red truck. But now at text time, I can compose multiple different energy functions together. So I can take a red truck energy function as well as desert energy function. And by jointly optimizing both of these, I now can get an image of a red truck in a desert. And in practice, we control the influence of each factor by scaling the magnitude of each energy function. So if you want your image to have more of a red truck property, then you would just increase the weight on that energy function a little bit more. So depending on what the energy function represents, there's an algebra in which you can really combine these energy functions. So if the energy function represents utility, adding the 2 energy functions corresponds to utility addition. If the energy functions correspond to sets, adding the energy functions correspond to set intersection. And if they represent probability distributions, this corresponds to the product of the distributions. And there are a variety of other operations I'll go into more detail next. So first, let's look a bit at the set membership energy function. So let's say I have an energy function for a blue set, so that all points in the blue set have low energy, and all other points have high energy. And likewise, let's say I have an energy function for an orange set, where all points in the orange set have low energy, and all other points have high energy. Now, if I construct the energy function where I add the 2 energy values together, this new energy function has low energy exactly at the points in the intersection of the 2 sets. So adding 2 energy functions allows you to sample from the intersection of 2 sets. In contrast, if I take the soft minimum of the energy function in the first set and the soft minimum of the energy function in the second set, now I get a new energy function that has low energy at all points in either the first set or the second set. And finally, if I take one energy function and subtract the second energy function, now I have a new energy function that has low energy in all points in the first set. That are not in the second, all points in the second set that are not in the first set. So essentially, this allows you to really combine these sets using logical operations. And you can actually nest these operations as long as you threshold the energy function afterwards. So let me give some examples of this. So in this setting, we trained the energy function to generate a gray cylinder behind a yellow cube, as well as a gray cylinder below a brown cube. And now by combining these logical operators, we can now generate images of a gray cylinder behind a yellow cube and not a gray cylinder below a brown cube. Or we can do something a little more complicated. So we can also generate images of a gray cylinder behind a yellow cube and a gray cylinder below a brown cube, which are these 2 images, or a gray cube a gray cube behind a brown cube and a gray cube right of a blue sphere, which are these right 2 images. So now we can do these more complicated nested sets. We can also use these energy composition operations to compose probability distributions together. So if you have an energy function for P1 of x, and you have a second energy function from P2 of x, by adding the two energy functions together, we can sample from the product of the two distributions, P1x times P2x. We can also sample from the mixture of two distributions. So if we have P1 of x and P2 of x, we can draw samples from the mixture of P1 of x plus P2 of x. And finally, we can draw samples from the inversion of one distribution with respect to the other. So if we have a distribution P1 of x and P2 of x, we can draw samples from P1 of x divided by P2 of x to the alpha. So the base operations of combining probability distributions has a lot of different uses that I'll just briefly go over. So one nice use of this is that it really allows you to generate these complex scenes. So if you have a text-to-image model, where the text-to-image model is trained on simple test sentence descriptions, such as a couch right next to the windows, then at test time, if you ask it to generate a scene of a couch right next to the windows, a table in front of the couch, and a vase of flowers on top of the table, this is pretty out of distribution from the model, and it is unable to generate a scene with all these properties. But by taking the product of distributions, where each distribution is conditioned on one of these text descriptions, now we can generate a scene with all three of these properties. You can also use a similar procedure to really adapt models. So you have a base video model that generates videos in a particular style. By composing it with a separate, or like multiplying it by a probability distribution for a particular style, such as digital art, outdoor videos, or storybook illustrations, now you can generate videos in that particular style. You can also compose these distributions over parts of an image to specify where you want objects. And finally, you can also use these probability distributions to represent constraints. So you can solve constraint satisfaction problems by just composing probability distributions per constraint. So those are a couple examples of how you could compose these models and use them for a couple of tasks. Now let me talk a bit about actually how to sample from these. So normally when we compose, so if we have a single energy landscape and we try to sample from the single energy landscape, as we compose these models together, the energy landscapes gets more and more complicated. So sampling also gets increasingly complicated because you get more and more local minima. So it turns out that you can make the sampling or optimization when composing a little easier when you use diffusion models. And the idea is the diffusion models learn a sequence of denoising functions, epsilon, where denoising function can be considered from time step 1 to time step t. And each of these denoising functions actually corresponds to energy landscape. So each one corresponds to the gradient of an energy landscape, where the first distribution the T's distribution is the normal distribution or Gaussian noise, while the first distribution, or like the final distribution, it corresponds to the original the target distribution P1 of x. So the diffusion model defines the sequences distributions, where you still have this Langevin sampling procedure, where this alpha t contracts you from one distribution to the other, because each of these distributions are defined on different scales. Now, if I want to draw samples from a product distribution, let's say P1 of x times P2 of x, one thing you could naively do is you can just take the normal diffusion sampling procedure, but you just add the two gradients. So you take the gradient of the first energy function and the gradient of the second energy function, and you can add those and then use the diffusion process to sample from the sum of those two score functions or denoising function or gradients of energy functions. It turns out that that actually isn't fully mathematically correct. So the diffusion process requires a particular gradient, where if you actually take the product of two distributions, that gradient isn't equal to the sum of these two individual terms. But you can actually implement compositional sampling from diffusion models by simply interpreting them as energy-based models. So now, so again, we take the denoising functions epsilon1 and epsilon2 for the two distributions. And we simply add these two together. And now these added denoising functions get you this sequence of energy-based models, starting from time step t, where it's the Gaussian noise, to time step 0, which is the target product distribution. And now, now what you can do is once you have the sequence of energy-based models, you can use annealed importance sampling to really sample from this final product EVM. So you initialize your sample from Gaussian noise, and you simply transition between each distribution by running multiple steps of Langevin dynamics. So you start from Gaussian noise, then you run a couple steps of MCMC sampling on the denoising function at time step t, then t-1, then t minus 2, and so forth. And you can actually implement this in a way very similar to normal diffusion sampling. The only difference is that you run multiple steps of the reverse sampling procedure at a fixed noise level before moving on to the next noise level. And this is used to really sample from the energy landscape, as opposed to being this like integration kernel that moves you from one noise level to the other. So with some small modifications on the diffusion sampling procedure, you can sample from composed diffusion models. And this is what qualitatively, this is what it looks like. So you have one energy function at the beginning, which is really smooth. And then you have the sequence of energy functions which gradually get sharper and sharper. Okay, so I've spent a lot of time talking about how we can compose energy functions together. One question I haven't really talked about is how you can actually discover these factors. So I'll present one way to kind of discover these factors, but I think there's a lot more research that can be done in this area. And one idea is that you can really represent the generative model with a factorized structure. So let's say I have a distribution P of X I want to model. Instead of just modeling it as a single model, I can just simply represent it in a factorized form. So I can say P of X is equal to the product of all these factors. And now let's say I have a task where I want to learn a distribution for reconstructing an image. What I can do is I can represent the probability distribution of the reconstruction of the image as a product of a set of independent factors I talked about earlier. And what this says is now I want to learn a set of energy functions given this image, so that when I optimize all these energy functions together, I get my reconstructed image. And it turns out that if you make this latent dimension relatively low dimensional, you can enforce that each of these energy functions capture different aspects of the image, so different parts of the image, because that's the most efficient way to encode the image. But the overall idea is just represent this distribution as a product of independent models. So here are a couple illustrations of this. So if we have an image of 4 objects, these energy functions correspond to individual objects in the image. Well, if we have a picture of a face, these energy functions correspond to parts of the face. So the facial appearance, the background, the hair color, and the skin color. And now if we optimize or sample from the product of all these energy functions, now we get a reconstruction of the face or a reconstruction of the 4 objects. And the benefit, and one really nice benefit of learning these components is that it really allows us to generalize. So let's say I have one model trained on a data set of spheres and cubes, and I have a second model, completely separate model that's trained on a data set of boots and trucks. What this allows us to do is we can compose 2 components discovered on the first data set with 2 components discovered on the second data set, which allows us to generate these hybrid images where you have both boots and trucks as well as in cubes and spheres. So even though we don't have any data of this form, by composing components together, we can generate new images with new combinations of objects from 2 separate data sets, which illustrates the power of composing parts together. Okay, great. So that was a brief introduction on compositionality. Now I'll talk a lot more about how this compositionality really enables you to do planning.
Yilun, may I ask a question about that compositionality? So one question there, the one thing that I missed was, how do you enforce orthogonality, independence, between these components? Because when you sum these energy models, you're assuming independence, and your model is an independent model, right? How did you enforce the independence? I missed that point.
Yeah, so we have no explicit way to enforce the independence, but what we do is we just constrain the latent dimension of each distribution to be really small. So the most effective way for each distribution to explain the image would be to capture orthogonal aspects of each image. But it would be interesting. I think it would be, we haven't really done this, but it would be interesting to try to like enforce some type of KL constraint between the distributions or like some type of mutual information to try to explicitly make these more independent.
Got it. Yeah, thanks.
Thanks. Great. Yeah, so let me now talk a bit more about how you can really compose these models for planning. So a lot of my research has been driven by the goal of trying to construct intelligent robots. And when we think about people, we can do so many different things. So if we want to make a BLT sandwich, we can do all these things such as cutting, slicing, as well as going outside and finding objects. And the question is, how do we gather robots that can likewise solve so many different tasks? So a lot of research has recently been on behavior cloning, where we just simply try to gather demonstrations of robot actions in the environment, and we just try to fit a single generative model on that data. And now a really big problem is there are a huge number of environments, and there are a huge number of goals. So how can we gather data that fill in the entire space of possible demonstrations? So in this section, I'll talk a bit about a particular type of compositionality that really allows you to more effectively use your data. And the idea is we can take our demonstrations and we can learn two separate generative models. We can learn one generative model that captures the dynamics of the world. So it captures what are feasible transitions in the world. And we can simply learn a second generative model that captures these are the goals of the world. So this corresponds to cutting lettuce, or this corresponds to finding tomatoes. And now by factorizing the distribution in this way, we can now cover a lot more space than the original demonstrations we've seen, because we can now stitch together the dynamics I see when cutting lettuce was the goal of finding a tomato. So because now one model just represents dynamics and one model just represents goals. Okay, so this type of decomposition between dynamics and goals has been done a lot. So this corresponds to model-based planning. And the idea is I have a single step dynamics model that takes in the state in action and predicts the next state. And we repeat this several time steps. And then we have a separate reward function, which at each state predicts a reward. And now to the plan, what I do is I simply optimize for a set of actions that optimizes the final reward. But in practice, this becomes a little difficult because optimization often leads to these adversarial states. So you often optimize for the set of actions that according to your reward function and dynamics model gets very high rewards, but in practice actually isn't really good in your environment. So I'll talk about one way to solve this. I'll talk about one way to kind of solve this issue by simply using energy-based models. And the idea is we learn an energy-based model over trajectories of distributions, so that if any pair of any transition state 1 to state 2 has inconsistent dynamics, the energy is high. And only if every state action pair has consistent dynamics is the energy low. And this helps you avoid this issue of adversarial states in model-based optimization, because we've explicitly shaped this energy landscape to have minimal energy at trajectories with dynamics that you've seen before. But learning this type of trajectory level energy function also loses some amount of independent structure. So let's say your environment is Markovian, and we have trajectories that are shown in blue and gray here. And what we really want is we want to stitch a trajectory that goes from this black dot to this star. But we can't do this because this is out of distribution, right? We have not seen this at the trajectory level. So we can solve this issue by also making this trajectory model compositional. And one way to do this is you can just structure this trajectory energy function to be energy functions over pairwise transitions. And what we do in practice is we encourage it at the architectural level by having the model be represented as a set of temporal comps. And we find that this allows us to generate these trajectories that go from this black dot to this star. So once we have this trajectory level energy function, we can use this compositionality to implement planning in the same way that we could do it in the image domain earlier, where now we have this one trajectory level energy function, and we have a separate energy function for what we want the behaviors of the model to be. So it can be a goal, it can be value functions, or it can be test time constraints. And now by optimizing this composition of these two energy functions, we can implement planning or reinforcement learning at test time. So let me give a couple illustrations of this. So first, we can solve offline reinforcement learning tasks using this composition. And the idea is we take an energy function for dynamics, and now we just take a separate energy function that estimates the rewards. So we just learn a reward function for a particular task. And we essentially just compose these two energy functions together. And by combining these two energy functions together, we now get a policy that can optimize this reward function. And the benefit of this is that depending on which reward function you compose here, now you can get many different offline RL policies for different tasks in a very modular way. And what we find is that this type of compositional approach is able to perform very comparably to the state-of-the-art offline reinforcement learning techniques, but it doesn't really require any of this dynamic programming or bootstrapping, and it's very modular. But the benefit of this procedure is that you can do a lot of things outside of just, instead of just offline and reinforcement learning. So another interesting thing you can do is you can take this energy function for dynamics, and now you can compose it with a separate hand-constructed energy function, where the hand-constructed energy function has infinite energy if the start state and go state are not the ones you specify, and otherwise has low energy. So if you compose these two energy functions together, now you have an energy function that samples trajectories that have dynamics similar to the ones you've seen before at training time, but which generate trajectories that have a start state and a go state. So what this means is that this allows you to essentially construct a zero-shot goal-seeking policy. So here we trained this energy function on just random interactions in this maze. And by just specifying the start and go state, by running the optimization procedure, we can now get these trajectories where the last one is a very long horizon trajectory of length 512 between the start state and go state. And we find that this procedure is able to dramatically outperform existing offline reinforcement learning techniques because the horizon is very long. And it requires no training, so it can be applied both in this single task planning setting where you have a single start state and go state, as well as this multitask planning setting where there are multiple go states and multiple start states and go states. And finally, what you can do is you can also combine these energy functions with cost functions. So you can just specify costs where these costs can be learned or hand constructed, saying what I want to do at each state. And here we have an energy function that's been trained to stack blocks. And we can hand construct energy functions specifying the order of blocks. So we can specify that I want the gray block on top of the purple one, the purple on top of the red, and red on top of the blue. And now at test time, you can now stack the blocks in a particular order. And you can also do this planning procedure when you're only given visual observations. So here you just have, so here the model just takes an image observation and then it generates a sequence of states and actions. And this allows you to, execute results on real robots. So here we had 50 demonstrations of placing the mug upright. And now by running this planning procedure, predicting the next sequence of actions, this model is able to place this mug upright. And you can also do this similar thing where you can use this to spread sauce on a pan. And a final thing is you can also do this compositionality in the space of images and text, where the idea is if I want to do planning across many different environments, often each environment will have a very different state and action space. So I can just represent these states and actions as images. So I can, instead of generating energy function over the future states and actions, now I generate an energy function over the future sequence of image states I want to reach, where I would then use a separate inverse dynamics model team for actions from these images. And what this allows you to do is now you can generate video plans of a robot picking up an object and placing it next to another object, as well as having the same planner be able to pick up a sponge and spread the table, as well as pick up silverware and drop it down. So you can have a single model that can do all types of different tasks, where here the goal is specified using natural language. And this type of video abstraction for planning also allows you to learn from the internet. So there are a lot of internet videos of opening doors. And you can imagine that the model, by seeing all of this information, can use this to also figure out how to open doors. And one thing to note is that these synthesized plans are highly detailed and real. So this is a synthesized plan of putting a banana in a pot or pan. But you can see the robot is able to pick up the object and really drop it. So it really seems like it understands, it seems like there's a lot of physical information in the video. And here's another example where you can see that it can actually simulate the closing of the gripper as well as dropping it. So you can imagine that lots of this information could be very useful for decision making. Great. So that was a brief introduction on planning. So finally, I'll talk a bit about multimodal models. And I noticed there are two questions. I guess I'll answer them at the end of the talk. Okay, cool. So now let's go to multimodal models. So let's consider a task of making a cup of tea. So this task requires a lot of sources of knowledge. So you need to have some type of common sense knowledge. So you need to know where to look for a tea kettle or the steps needed to steep tea. You need to have some visual knowledge of the world. So you need to know the properties of objects as well as the 3D geometry. You need to have some physical knowledge of the world, yeah, how heavy things are, as well as some type of control knowledge on how to pick up the objects. So if we want to really get a robot that can make a cup of tea, the problem of generalization is even harder because now I have to get demonstrations showing the robot how to make this cup of tea in all types of environments with all types of objects, all types of physics, and all types of visual information. So what I'll talk about in this section is how we can actually, instead of trying to gather these very long horizon demonstrations for these tasks, we can actually combine existing foundation models together. So we can use large language models, video models, and action models, and we can really compose them in a zero-shot way to solve these tasks instead of requiring all this data to solve the long horizon demonstrations by itself. So we need a little bit more terminology or like methodology to really combine foundation models together. So the overall idea is that in general, you can treat this energy function as kind of a loss function in the sense that if you have a pre-trained model, we can convert a pre-trained model into an energy function via a loss function. So if we have a large language model, which takes as input a language, then the likelihood loss can be used as an energy function for the language model. So if the likelihood loss is low for that sequence, then that means this input language is in distribution. And if likelihood loss is high, then the input sequence is out of distribution. And in a similar sense, if we have a clip model, if the language and vision alignment loss is low, that means the language and image match, and otherwise they don't match. So in general, you can take any foundation model and convert it into an energy function via the training loss it was used to via the loss that was used to train it. So let me show a practical example of why this is useful. So let's say we have a vision question answering question where the question is, what is a cat doing? And you have this corresponding image of a cat. Now, if you directly try to solve this task using a language model, it can't really do it because it can give you answers to the question, but it can't see the image. In contrast, if you try to solve this task using a clip model, it also cannot do this task because a clip model cannot parse the question. It simply sees the image. But we can actually combine these two models together to be able to solve this vision question answering task. And the way we do this is we just formulate the response, generating the response X is minimizing the clip energy function. So getting a response that is well aligned with the image, while also minimizing the large language model energy function, which is getting a response that's high likelihood under the language model. So if we get a response that minimizes both of these energy functions, we have solved this vision question answering question. And then there's a small caveat where in practice, we don't actually have continuous gradients to optimize large language models. And for text, there is no continuous gradient. But we can use a similar idea that I talked about at the beginning of the talk, where you can really use one generative model to help your optimization. And the idea here is now we simply draw samples from the large language model, and then we find samples that minimize the first energy function, which is clip. And then we use these better samples and ask the language model to draw new samples based off the sample, and we repeat this procedure where we're now using the large language model to help you guide your optimization procedure. So here's an example. So at the beginning, the large language model might say something like the cat is catching a mouse. Then by running some steps of optimization, the model will say the cat is walking into a house. And after running all the steps of optimization, then the model will say the cat is walking in a yard. So you can essentially view this type of energy optimization between two models as a way to like construct, combine information or constraints across the models at inference time. So now let me go back to the task of making a cup of tea. So to make a cup of tea, we need to think, if we try to directly use a language model to solve this task, it can tell us to look for a tea kettle, to heat the water, or find a tea bag. But this isn't sufficient to solve the task because these instructions are not necessarily grounded in the environment, and the model doesn't tell you how to actually execute them in the environment. A large video model can synthesize a video plan like this when you tell it to like pour a cup of tea. So it can give you a lot of information on how exactly you want to pick up the tea kettle and pour water, but it doesn't really tell you the high-level steps needed to solve the task or the low-level control. And similarly, a goal condition policy can tell you how to actually, the precise sequence of controls to actually pick up an object, but it doesn't have any of the high level information that you want to solve this task. And one idea is by composing these three generative models together, we can actually combine the information across all of them. And the idea is we want to find a text plan that is highly likely under the language model, as well as the video model. And if the text plan is highly likely under the video model, that means it can synthesize an image plan from the starting image, which means that the text is grounded in the environment. And similarly, we want an image plan that's highly likely under the action model, which means the action model can synthesize an action given the image plan. So by finding a text plan, image plan, and action plan that maximizes the likelihood of all three of these models, we get a plan that satisfies the constraints across all three of these models. And to actually optimize it, what we do is it's the same procedure that I talked about earlier. So you take the large language model, it samples several different language plans. Now the video model chooses the one that is the highest likelihood, and that becomes the one that you use for the language plan. And now the video model samples a series of video plans, and the action model selects the one that's the best, and that's the one you use for the video plan. So here's, and so you can view this composition as a way to construct the planner across all three levels. So here's a worked out example of what it looks like. So let's say I have a goal of stack a red block on a cyan block and place a brown block to the right of the stack. Now the language model at the beginning might say something like place a cyan block in a brown box, which is reasonable. But in this environment, there is no cyan block. So now the video model will just synthesize something that is inconsistent, and it will have low likelihood for the video, telling the language model that this is not a good language plan. So then you continue to sample the language plan until you get an instruction that is consistent with the environment. So in this case, in this environment, if you place a white block in a cyan bowl, it becomes colored. And now this becomes a reasonable plan in this environment, and this is the plan you execute. And by nesting all three of these models together, you can eventually construct this overall goal of stack a red block on top of a brown block and place a yellow block to the left of the stack. So this is done by just composing these three models together across all three levels. And just the final thing is in practice, this type of consensus procedure between this language model and video model is a little slow because the language model will oftentimes generate these plans that are not grounded in vision. So you would need to keep sampling until you get one that actually is possible in the image. And the video likelihood can be not the best objective to optimize. So one way to try to solve this issue is you can make the models that you compose be a bit more cross-modal. So in this case, instead of having a language model, you can have a vision language model. And now the vision language model can propose more visually grounded plans, as well as propose a heuristic, as well as like give you intermediate feedback to tell you how much progress you've made toward this task. So what does this mean? So now let's say I have a goal of put the fruits in the top drawer, and I have this image shown here. So now the vision language model will propose two possible plans given both the text goal as well as the image, where here the model would predict things like place a banana in the top drawer or open the top drawer. And now in this, similar to the previous setting, the video model will take this image as well as this goal, place the bananas in the top drawer, and it will try to generate a plan for that. And in the case where there is no top drawer that's open, it will just drop the banana. In the case where there is a drawer, the video model will synthesize open the drawer. Now the difference is instead of using the video likelihood to choose the best language instruction to execute, now we use the vision language model to estimate how much progress you've made. So now when you have this video plan, when you pick up the banana and drop it, the vision language model will say this is not much progress, and it will give a poor estimate of this. And in contrast, if the plan becomes opening the drawer, now the vision language model will predict a much higher progress, and then the heuristic estimate will be higher. And when you have these three models, then you can actually implement planning using all the composition of these three. So now what you do is you just sample. So you have this instruction, put the fruits in the top drawer. Oh, oops. Put the fruits in the top drawer. And now the vision language model will sample two plans, open the top drawer or place the banana in the top drawer. And then we'll select the most promising one. And then you repeat this procedure where you take the final image state. Now the vision language model proposes the instruction, place the banana in the top drawer, which you pick. And then it proposes three possible actions. Close the top drawer, place the apple in the top drawer, or place the Coke candy in the top drawer. So you render each of these videos and you select the most promising one. And you repeat this until you get this overall plan for the whole task. And it turns out that you can take existing zero-shot foundation models. So you can take a POMI model, a video model, and a go condition policy. And by just composing these in a zero-shot way, you can solve new tasks where none of these models have been explicitly trained to solve this task. So here we have the task, put the fruits in the top drawer. All three of these models were trained on other tasks, but by composing them, you can have these models pick up objects as well as place them in a drawer and then close it. And then finally, if you have a goal, make a line. This procedure can predict a sequence of instructions, such as move the red circle to the left, the yellow hexagon, move the green circle closer to the red star. So you can have these kind of detailed language plans, and then you can synthesize this entire video plan. So this is completely synthesized, but you can see that the approaches can like really align all these objects until you have a full line. And you can see there are some aberrations in the physics, but it conveys making a line. And you can also convert this to real robot execution. And overall, we find that this compositional approach allows you to solve long horizon tasks much better than existing baselines, such as end-to-end action policy, a hierarchical policy without planning, or like a large video model. Okay, great. So overall, I've talked a bit about in this talk about how like we can use this idea of compositionality across a variety of settings to enable you to generalize in planning across multimodal models as well as in the image domain. Thanks everyone so much for listening, and I'm happy to take any questions. I guess I should also probably answer the questions on the Q&A, but I'm happy also to take any other questions.
Thank you so much for the very clear talk. I really appreciate it and enjoyed it. Yeah, there are two questions in the Q&A. Let's start with those.
Okay, great. Yeah, where do you position? Okay, so first question is, where do you position your work with respect to the mixture of experts, learning literature? So, I mean, I feel like all these works are a little, they're all a bit similar. So I would say my work is one way to like is a framework for composing models together using this idea of energy optimization. And the mixture of experts is a different way to really combine different modules together using more of this like routing procedure. So I think they're just different ways to implement compositional models. And I think the overall idea of compositionality is very important because I think it allows you to really generalize better because it encourages you to like learn modules. So yeah, I would say that they're just like different implementations. You could imagine combining them together. Like maybe each of these experts could also be energy functions. So lots of connections. And then I think the second question is, what do you think? In which cases we can use compositional generation? So I think actually, you can definitely use these models for software agent-based systems. So you can imagine that you have one model that like parses this, maybe parses the final goal that you want to solve. You have one model that like makes routines for like fixing the program. Like you can imagine for each part of the software agent, you have a different model. And I guess there's a lot of work on these more multi-agent software systems. And you can imagine that each of these agents here is a model that you compose. So I think like you could definitely like I think there's also so I didn't have a time to talk about this in this talk, but we also have some work where you combine language models through this more multi-agent debate or like multi-agent communication, and then you can kind of interpret this as composing each of the likelihoods of the models also, where you're using the text as a way to pass messages between the models. So you could definitely imagine that each of the modules in the software agent is just each of the models we've talked about here.
Fantastic. If there are any other questions, please post them on the Q&A from the panelists. While everybody is preparing more questions, I have one. So the energy functions, when you combine these as a summation, I wonder how sensitive is the scale of these energy functions, right? I think you mentioned at some point that you scale these energy functions and like how sensitive is this approach to that scale? Because it can be arbitrary, right? Like when you train an energy function in one domain, the scale is really not clear, right?
Yeah, definitely. Yeah, and so you would need to in practice you would need to really you do need to tune that hyperparameter. I guess you could imagine it's kind of like test time optimization. Like you have your test time metric or objective you want to optimize for, and then you would tune the skill until you get behavior that matches the objective as best as possible. But you definitely do have to tune the parameters depending on because otherwise, especially on different domains, or you combine them over different inputs, the skills are very different. So yeah, that is a big thing you have to think about when combining these models.
Got it.
Okay, thanks for the great talk. I guess the one question that I had was, so a lot of these examples, you were kind of focusing on the conjunction intersection, and you had mentioned some other things like set difference. I was wondering if you have any like experience empirically looking at performance for these other types of like logical situations.
Yeah, so I think we have some experience. So in the text to image setting, let's if you want to generate very high quality images, it's important that you want to make sure that the images are not blurry, that they don't have like illicit content and settings like this. And here you can use this like logical not operation to do that. So you can say generate image of the thing you want, but make it not low resolution, make it not blurry, make it not low quality. And we find that really helps you improve the image quality that you generate. And I think this has been used a lot now for a lot of like this is referred to as negative prompts, but people use it a lot to generate high quality like AI generated art. So we find that this type of negation operation is useful when you want to avoid generating things with a particular property.
Okay, and I guess a follow-up on a different type of direction is yes, maybe not so much of a follow-up, but so I guess I was wondering, like the empirical comparison of taking a traditional non-compositional approach when you're in distribution, does it degrade at all compared to traditional approach?
Yeah. So if it's in distribution, it's something you've trained on. And like you've built this compositional structure. Unless the compositional structure is exactly what's inside your data, it's going to be a little worse because it's biased. You're imposing like arbitrary structure on the data. I guess for a lot of settings, like in robotics or embodied agents, you don't have that much data, in which case now the compositionality is very useful. But yeah, if it's in distribution and you have lots of data and you don't know the exact ground truth structure, then probably a non-structured approach with a lot of data would perform better.
Okay, it's almost like a piecewise situation of determining how far out of distribution a setting is to which model would be used.
Yes.
Okay, yeah, thank you.
And there is one more question in the Q&A. I mean, yeah, if I want to summarize it, it's in a little bit domain specific, but the core at its core, the question is, what if the distribution has highly dependent factors? Like in drug discovery, it seems like that's the case.
Yeah, so you don't so I guess in my illustrations I always draw the factors as completely independent. In practice, you don't have to make them independent, right? You can actually make the factors Markovian. What I mean by that is let's say you have like 20 variables, right? You can have one factor be 5 variables and you can have another factor be 5 variables and you could so you can imagine that for all the variables that are correlated, you can just have a factor for those correlated variables. So if everything in your drug discovery is completely correlated, then I guess it would be very challenging. But I guess probably no method would work that well if it were completely correlated. But I think you can still get the factors to be like parts of the parts that you think are correlated. Yeah, and I guess actually there was maybe oh, I guess there's another question also. Should I... Okay, so let me read the other question. The method from first for me to understand what's going on. How is the energy defined for the factors to be learned? Well, okay, so the energy function, so overall, like normally when we learn these energy functions, it's usually probabilistically. So the energy function is just log likelihood of the log likelihood of the data. I wonder. And then how continuous are they? Say, imagine that generalization will be combined. Yeah. So okay. So it's true that if you learn a set of factors, right? Then the generalization you get is dependent on how many times you can compose the factors. So I think one thing is that let's say you have like two features and you have three factors. It turns out that you can actually compose them in more than 9 ways. Because what you can do is you can compose well, it depends on the setting you have, but like you can imagine that for one feature, you can compose it several times and compose several elements of that feature together before composing the other feature. So I guess there are a variety. So there are more ways. So you can actually nest this feature composition. And the question is, how continuous is the compositional dynamics between factors? So if you have something between green and red, or a place between X and Y. So what we find is, let's say you have something like green and red. So let's say you want to make an apple of a green apple, and then maybe you also wanted to make an image of a red apple. So these are at odds with each other. So we don't, I guess because the models are just like likelihood models around each of these operations, they don't actually interpolate that nicely. So you wouldn't get something in between a red and a green apple. Rather, you would get some type of optical illusion where parts of it look red and parts of it look green. So I guess they're a little continuous, but maybe not in the way you would expect.
Yeah, and given that we are over time, maybe one more question. I think the question is with respect to motion planning.
Okay, sure. Yeah, okay, let me just read out the question. So can you speak more on the composition of functions in the motion planning setting? How would you go about learning energy functions for different configurations of obstacles, such that you can deal with out-of-distribution configurations? Right. So we actually have this paper called Potential-Based Diffusion Motion Planning. But the idea is that in the motion planning setting, you can imagine that you can represent an energy function per obstacle or per part of a configuration space. So that now if you have more obstacles or a different configuration of obstacles, you would just compose these obstacle condition potential functions together to specify that new setting. So this allows you to train your model with 3 obstacles, and at test time generalize to maybe 8 obstacles, or it can generalize also to concave obstacles, because you can just represent the concave obstacle as a composition of convex obstacles. So by learning a potential function for obstacle avoidance, composing them can allow you to generalize.
Fascinating. Awesome. Thank you so much for this great talk. I think we all enjoyed it thoroughly. And thank you for your time, Yilun. I hope a good rest of your day for you. And yeah, hope to see you at the upcoming conference soon.
Yeah, thanks so much for having me.
Thank
really
you.
great. Okay, see you. Bye.
Thank you.